So welcome to the afternoon session of the first day. So our first talk today is by Professor Aprameyo from HRI, who will speak on p-adic Artin Formalism for the triple product of modular forms.
Yeah, thank you. Yeah, thank you to the organizers for providing me with this opportunity. Yeah. So it's a very nice place. I mean, it's my first time at ICTS, so it's a really enjoyable last week and also I hope this week also. Yeah. Okay, so I'll not write anymore the title. I mean, it's like as Professor Ghate said, it's p-adic Artin Formalism for the triple product. So I'll start with the introduction. So yeah, I'm audible, right? Okay, so I'll start with pretty basic definitions. So like consider a Galois representation of dimension n over some topological field F, such that it's essentially you consider the Galois representation like this. So my idea is to attach some canonical way, some L functions towards the like arbitrary Galois representation. So let me be more specific. So let's take K and F like some number fields. And I consider like some specific case, like K over F is finite and Galois. And one considers like rho, it's a Galois, absolute Galois group K over K, and if it factors through the finite Galois group, like over K over some F, and to GLN C. So then these Galois representations which have like finite image, these are called Artin representations. So to each such Artin representation, which an Artin representation rho, I will recall how to attach an Artin L function like L rho S in the following way. So I define like L rho S, and let me say something more. I mean, let me say that this we can also consider as GLV for some n-dimensional complex vector space. So I define L rho S like LVS as product of P prime in K as some local L function. And what are the local factors essentially? So let me be more precise, LP. So where LP rho T, this is, yeah. Yeah. Yes. Yes, yes. Yeah. Yeah. So at L rho T is essentially like determinant of 1 minus T acting on the Frobenius and rho IP. That's where IP is the inertial at P. Okay. So I mean, one immediate example one can see is if rho is a trivial representation, then LP rho T, this is nothing but 1 by 1 minus T, and then the L function, this is nothing but the zeta function. So similarly, one can do for like for elliptic curves, or like in general, like automorphic forms. One can also define the L functions in this way, associated to the corresponding Galois representation, which I'll come in later. I mean, what Galois representation I'm talking about. Okay. Yeah. So, I mean, these are really like still pretty standard. So, what is the Artin formalism? So, like, again, I am in the case, let's say, case B Galois, and one consequence of Artin formalism says that if I consider L function of rho direct sum rho prime, that's also like a Galois representation. And then this actually decomposes as L rho S times L rho prime S. That's pretty standard. Okay. So then, like conjecturally, one can associate some p-adic L function also associated to the given representation rho for arbitrary rho up to some interpolation properties. So if you believe like the conjecturally the existence of like the p-adic L function for arbitrary Galois representation, then this gives a natural question to ask is, so is like the p-adic L function rho direct sum rho prime, whether this can be also factorized as LP rho times LP rho prime. Okay. So given, I mean, like you have to also, of course, have to have the existence of all the p-adic L functions, and of course, I have to give some meaning, like what do I mean by equality of p-adic L function? So up to maybe some p-adic unit. If this is true, then this is what I mean by like p-adic Artin formalism. Okay, so essentially, like given a Artin formalism, all the global Galois representations. So if the complex L functions factorizes naturally, the question is to ask is whether this factorization carries over to the p-adic L function. Of course, you have to have the existence of all the p-adic L functions and everything. So let me first recall some known cases. Okay, that's the next section. So that's my guiding question in some sense, like whether the p-adic Artin formalism will work for triple product of modular forms. But let's first recall some known cases. So the first case, what I want to recall is a famous result by Gross. So suppose K is a quadratic imaginary, and P splits in K completely. And then let chi be a quadratic, you don't need to assume. So let chi be a continuous representation, like a character essentially, of Galva of K mu infinity over Q. It's a p-adic character, essentially what I'm taking. And also let chi K, you take the restriction of chi to Galva K infinity over K. Then we have the complex L function factorization, which is like L of I K. I take the infinity part S. This is L I infinity S times L I infinity, some quadratic character which is associated to the quadratic field. So where epsilon, the quadratic character associated to. And this is standard, like it just decomposes like this. And then what Gross proved, the corresponding p-adic L function, like LP chi, this is actually product of chi times P chi epsilon. And here the p-adic L functions are like Kubota-Leopold p-adic L function. Yeah, sorry, this is Kurtz, yeah. And this is Kubota-Leopold. Yeah. So now one should immediately ask is like when I have when I have the existence of the p-adic L functions, and as is clear, like this should have some interpolation property, and this should really interpolate the globe. I mean, like the complex L function. So isn't it like really obvious if the existence of p-adic L function is there? I mean, that kind of, it's almost like tautological if what I'm saying and the existence of the p-adic L functions are known. But that is really not the case, because sometimes what happens, I mean, the interpolation regions between the left-hand side and the right-hand side, they might not coincide. So essentially here, when I'm talking, I mean, here I'm really vague. So I am not, I mean, I have to take evaluate and some character, and then the values what are given, these really don't coincide. It's outside the interpolation region sometimes. You really have to take help of some kind of Euler system argument in this case. But it is also true, like in some scenario, which I'm now going to state, maybe the interpolation property is enough, of course, given the existence of the p-adic L function. So that will be my next example. Any questions here? Yes. Yeah. It's equal up to, I mean, it's in lambda star. I mean, yeah, I guess. I mean, yeah.
Okay.
Otherwise, yes. There is Kubota-Leopold, you can't, I mean, it's like you have to give meaning of this. So if you can give meaning of, like, let's say, continuous character interpolation, maybe then it can be extended, but I don't know.
Mm-hmm.
Yeah.
But it said mu p infinity. That's why I was. Or does that say mu p alpha?
No, it's mu infinity. Yeah. Yeah, but I have to assume that, yes. Yeah. Okay. So the second case is like, let F be a classical eigenform of like k plus 2 gamma 1 n, like of weight k plus 2, which is greater or equal to 2 of level n with some with some Neven-Typus. And I will not define there are some conditions, some technical conditions like finite slope and everything, which I don't want to recall. And you again take K to be some imaginary quadratic field. And let F is a, you just take F is an eigenform and like some new form with without the like Cm by K. Okay. And yeah, and consider these local conditions, which I am not really telling, and consider its base change to K, which I denote by, let's say, Fk. Then again, like the Artin formalism will tell you the L function f over k s, this actually factorizes as LFS times LF I k over q s, again where I k over q is the quadratic character. Okay, so this is again pretty standard, but the important result is recently, I mean, there were some already some results earlier towards that direction, but the most general result one can say it's by Chris Williams and Salazar, like so they proved that if you take the LP cyclotomic of f over k s, so what do I mean by cyclotomic? Like you can construct, they construct some p-adic L function on the eigenvariety, and then they take like the restriction to the cyclotomic line. So that's the cyclotomic part essentially. This is equal to like two product of two major Kitagawa p-adic L functions, LPF times LP fi. So this is really like the GL2 version of what Gross has proved. Okay. So this no, I don't have to assume. Actually, even if you don't assume, then there are other results due to other authors. Yeah, I'm just, since I am not trying to recall all the results. But you're correct, yes. But the important addition, what they could do is they could now prove for finite slope cases. I mean, all the earlier results were ordinary cases. Okay. Yeah. Yes, yeah, that's what I was going to remark. And for finite slope, this, as I was telling in the Gross case, it doesn't follow from the interpolation, but here Of course, you have to be careful with the period computation. But once you know the exact periods, then this follows really from the interpolation. Yes, this is f times chi, like f twisted by the chi, yes. Okay, so this kind of gives you some ideas about the GL2 case. And now let me proceed towards GL2 cross GL2 case. This is a very famous result by Dasgupta. So that's the next case. So this is by Samit Dasgupta. So here I again start with like f in sk, gamma 1n, new form. And let me here also assume with some character. This is really general, yeah. And also assume some character like psi with Neven type is chi psi. So it's like some Dirichlet character. Okay. So what he considers is like the L function of LF tensor F and then a GL1 twist like this. So again here, like the Artin formalism will give you that this again decomposes as LF, L sim square F twisted by psi S and with then F and like, let me say psi F psi and S minus K plus. Okay, so this is essentially like, this corresponds to like 4-dimensional Galois representation. And here you have like 3-dimensional. And here you have like 1-dimensional. Right? So this really match up. I mean, this really like decomposition of Galois representation and you get it immediately. So what Dasgupta proved is one can have a factorization LPF F psi again up to some p-adic unit like LP sim square F psi and LP something like this. Huh? Psi is like this Dirichlet character and chi F is the like, I did not say. Chi is like chi F chi prime, where this is like the P part essentially, yeah. Like that's the P part and chi F is essentially like the, yes, this yeah, under ordinary assumption, of course, yes. Yeah, this I was going to say, yeah. So P part and the prime to P part. Where is chi psi? It's chi F times psi. That's the like conductor of, no, so sorry. This is n psi. Yeah. Yeah. So then what are these p-adic L functions? So this was actually constructed by Hida. This was constructed by Coates and Smith. And this is again like Kubota-Liu. Okay. So here, now again, the question should be asked like, does this follow from directly from the interpolation of this one? But it really doesn't, because here you don't even have like the interpolation properly for this. There's no central value. So you can't get like directly interpolation. I mean, that doesn't make any sense. So here also what one has to do is here, this has to be related via some Euler system of Beilinson classes. And in this scenario, you have to relate this with some kind of elliptic units. Essentially, it boils down to comparison between two kinds of Euler systems, and then you get it like this. Yeah. So one natural question, what one can ask is, what's the benefit of this kind of factorization? So it gives really, like, as a consequence, one can prove some exceptional zero formulas due to Greenberg. So that's a very nice consequence. Okay, so like this really kinds of tells the story about GL2 cross GL2 cross GL1, but let me ignore the GL1 twist. No, here there is no non-CM assumption. Here the only assumption is the ordinary. So so that's the next case. Like, what about like GL2 cross GL2? So that's actually the objective of my talk today. So that's the next section, like triple product of modular forms. Okay, so any questions still? Yeah. Okay, so let me now start defining some objects for the triple product. So let F is in like SK nu with level n, G is in like SL nu n, and H is in like SM nu n, like three normalized new forms of weight K, L, M, N, where I assume N to be square free. That's a strong assumption I'm making. And for simplicity now, we take like every eigenform has like equal level, all are in N. So then one can define this triple product of modular form like LF S. This is like the direct Rankine L series. So essentially this associated to the triple product of the Galva representation VF tensor VG tensor VH, where these are like the compatible system of Galva representations associated to each modular form. So that's a known construction. And then you can complete the L function by adjoining some Archimedean factor times the, and then this actually satisfies a functional equation like LF GHS is some epsilon factor times lambda FGH 2C minus S, where C is essentially like k plus L plus M minus 2 divided by 2. That's like just the standard construction. I mean, I'm not going to talk about in detail, but here there is a notation which is quite important, like the triple of weight, the triple of weights KLM, this is called balanced. So the triple of weights KLM is called balance if K plus L plus M is greater or equal to like twice the maximum of individuals. Yeah? KL. Okay. So why I am caring about balance? Let me continue, because this will give me like two cases which somehow relates to something what today in the morning Lai was speaking about, this coherence and incoherence condition.
Excuse me.
Yeah.
I assume something for level structure. Is it gamma 0 or gamma 1? Which is modular forms?
It's here. It's gamma 0.
Gamma 0. Okay.
Yes. Yeah. I don't have any.
No Neven character.
Yeah.
Okay.
Yeah. I'll specify where I am not using this. Yeah, but let me write this down with trivial Neven types. With trivial Neven types. Yeah. Okay, so I mean, then like the epsilon factor, this will be essentially like product of the local epsilon factors. And of course, every local epsilon factors is like plus minus 1. And then I'll define like, so B is here including the Archimedean prime also. So I say like FGH, this is essentially like minus 1 if KLM is balanced, and plus 1 if otherwise. Okay. And moreover, assume that I am in a balanced situation, like KLM is balanced, and I define like a sigma prime set of primes Q dividing N such that the local epsilon factor at Q, this is minus 1, this has odd cardinality. Okay. So if this is the case and I am in balance, then the Archimedean epsilon factor is minus 1. So this gives me the global epsilon factor. This is plus 1. Right? So essentially, this will imply that the completed L function, this does not vanish for any sign reason at least. Okay. And this is what I was remarking. So this balanced, like this epsilon is plus 1. This corresponds to today in the morning case. This is like the coherent case. And then I will go to the next case, which is unbalanced, where epsilon, the global epsilon factor is minus 1. And this will, what it was told in the morning, it corresponds to the incoherence condition. And as you saw in the morning, somehow this coherent case was a bit simpler. This is what it's going to happen here also. Like under this condition, I will get the factorization of p-adic L function for the triple product much more simplified way compared to what happens when the unbalanced region. Yeah? So that's the next goal. So let me still continue with the balance thing, and I'll try to give the main result where what I'm trying to say. Yes, yeah. I mean, even when you don't have square phi, there are computations, but it becomes much more, it's not so clean. Yeah. Yes, yes, yeah. Absolutely, yeah. Okay, so now let me still continue with the balance case, but I will make it even more simplified. So now assume like F is in weight 2k nu modular from n, and G is in like sk plus 1 nu n, and G is equal to H, like H is also like this. So essentially what I'm considering is like lambda F G tensor G. Okay. So that's the central L value what I'm considering. And now this, I mean, since like VLG, tensor VLG, this actually decomposes as sim square VLG, direct sum determinant of VLG. So like again, this is like 4-dimensional, and this is like 3-dimensional, and this is 1-dimensional. So now you take tensor with VLF. So this, that's the again Artin formalism. So this decomposes as lambda F tensor sim square G S times lambda F, and since it's determinant, you have some twist S minus K. Okay. So the goal is to find a factorization mimicking, let's say this is star, like a p-adic factorization of star. So I'm still in the balanced case. I mean, this factorization, of course, holds for balanced or unbalanced. Here, I don't need to assume anything. But let me be still in the balanced case here. Okay. So, yeah. Oh, because now I am taking like, it's, yes. Exactly, yes. So it's now essentially this guy is 8-dimensional. And this guy is like 2 times 3, like 6-dimensional, and this is 2-dimensional. So it matches perfectly. Okay, so before stating the main result in this case, let me define some, some more notations. Yeah, any questions, please? Okay, so let O be like ring of integers of some finite extensions of QP. And yeah. Yes. No, I don't understand the question. So this is like this Garrett-Rankine L function, right? What I defined. This is like the L function associated to the 8-dimensional Galois representation. So this is exactly at the L function level. Yeah. Yeah. No, that's fine. Yeah. Okay, and yeah, let gamma is 1 plus EZP.
Excuse me, I have just question on this balance case. I
Yeah.
just forgot. Sorry, I'm here.
Yeah.
And what kind of complex period is coming in for the algebra in balance case? I just forgot.
Yes,
the-
I'll tell you what.
Okay, you will explain
so it's,
later.
yes.
Okay.
Because this will be, I mean, it's a works by Minglung She. I mean, he constructed the balanced and the unbalanced p-adic L function.
Yes.
And like when I will give the factorization, there
Mhm.
I will tell you explicitly what's the period is.
Okay.
It's, I mean, I can tell now also, it's actually very nice. So it's like FF, GG, and HH. So if you take like, so this is like in QFGH. Like if you formulate the like Fourier coefficients if you attach, and then this is rational. Like this is the Deline's conjecture in this. No. Yeah. Yes. Yeah. Yeah, but this I'll come later again. Yeah. So yeah, so let's gamma be 1 plus PZP, then consider the Iwasawa algebra, lambda is lambda O, like ZP 1 plus PZP. And fix an isomorphism between C and CP. Yes, P is odd. Thanks. P is odd. Yeah. That also I'll assume later. Yes. Yeah. I have nothing super singular. Everything is good. Yeah. And let me also assume good ordinary. And what more? Yeah. So also consider the weight space. W like home O continuous on the CP. And I'll consider the classical weights inside the weight space, like the classical specializations. And suppose F and G be Hida families of ordinary destabilized new forms of some tame level n. Okay. And also consider like the RF, some like finite integral domain lambda. I mean, like extension over lambda. And then some more notation. Sorry for this. You also denote like WF is essentially the weight space of RF. And unfortunately, I need to extend the coefficients of the algebra RF, which is like RF, you tensor over lambda, some sigma with the Iwasawa algebra, and where sigma is essentially like an O algebra isomorphism lambda to lambda given by like sending t to t square. So why do I need this? Because I want to consider the R algebra. So consider the R algebra, the sigma algebra, R, which I define by RF, RG over lambda. So that's why I somehow need to extend the base, because this is how by Darmor or Jar actually used. So I'm just following that sense. And then finally, I considered the weight space associated to this R, which is like WF tilde cross WG, which I can now consider. I mean, this is, okay, let me first say what this is. This is like set of weight k lambda in WF classical times WG classical, such that weight of k is 2 weight of lambda. Okay. And if I have this definition, then I have like a natural embedding of WR inside the triple product of this. So WR you can embed in WF cross WG cross WG. So finally, after all these notations, what I want to say is I can construct some p-adic L function on this weight space, which can be thought as like a p-adic L function also on the triple product. That's the thing, what I'm trying to say. So that's what you should remember. I mean, forget about all the heavy notations. Exactly. Yes. So for for example, Minglung She doesn't have to do this because it was FGH. Okay. So then now I can finally state the main theorem in this case. So this is a joint work with me and Carlos de Vera Piquero, and then finally Carlos de Vera Piquero and Daniele Casaza. So what it says is like, assume the balance case, like the epsilon factor is +1. This is, I'm still considering the epsilon factor on the family. Okay. Then there exists a factorization as following. Like you have a balanced p-adic L function. Square is up to some p-adic units, like LPF m square G. Sorry, these are all in families. Times LPF. Okay, so the first thing is, what are these objects? Like this is, as I was saying, this is constructed by Minglung She. This object is actually constructed by us, and this is some kind of Major Kitagawa. Or like also we can use Greenberg-Stevens. So this really holds in the balanced case. That's the main theorem here. So let me give you some idea like how one can prove this. Yeah. Sorry. Yeah, so I'm running out of time, so let me say like how can one try to prove this. Let me come here. This is really yes, because that's a very important question. Because see, classically, what's the classical factorization? It's this one, right? This L function of f, g, g. So it comes from some kind of period formula. So the p-adic period, which interpolates this one, it actually interpolates the square root of this. So you have to essentially take the square of the p-adic L function, which will then interpolate the L function. Yeah. So that's why the square is there. And yeah, let me give you some sketch how this one can prove. I mean, so essentially for proving this, the important thing is to construct the p-adic L function. That, I mean, p-adic L function for the GL2 cross GL3, like this LP F sim square G. That is the main object. So how does one attempt to prove this? This really comes from, again, as today in the morning, Lai was telling some general picture. This is like the Gann-Gross-Prasad picture. So first of all, how do I prove this? This I will prove on the specialization at all classical points. So essentially, I can just take the classical modular forms, and then since the classical weight space is dense in the Hida family, then I can get the full result. That's the idea. So the first formula, what one can show is like lambda f sim square g at weight 2k. So this has a very explicit central value formula, like 2 power k plus 1 times product p dividing n, p plus 1 square, and divided by n, times quotient by ff and hh. I'll define what is h, and times like Peterson product of some Saito-Kurokawa lift restricted to the h cross h, and you take product like this and this square, and modulo g square. So so what is h? So h is essentially a half integral weight gamma naught of 4n. So this is like half integral weight associated to f. This is like the Shimura lift, and capital F is like the Saito-Kurokawa lift as a Ziegel modular form, like Saito-Kurokawa lift of F, okay, or H also you can say. So this is really explicit. I mean, how does one? So this is a earlier result by me and Carlos. So what one essentially does is essentially like doing explicit calculation of like Ichino-Ikeda type formula for the case like you consider SO32. So this is like where the Saito-Kurokawa lift lives, and you consider GSO4, where then you take the restrictions of this here, and then essentially you get like the global period factorizes as product of local period times the L value. And then essentially we have to by hand compute the local integrals, and this gives you this. So here now, let me just say something more, like you choose a fundamental discriminant d less than 0, such that the twisted L function does not vanish. Then via generalized Kunin formula, this gives me again a formula like FF divided by HH. So essentially I will try to replace this. This is essentially nothing but some explicit constant times lambda this k by CHD square. So where CHD is the dth Fourier coefficient of H. Okay, so that's a very well-known formula. So what happens then? Then I can choose some Shimura period C plus minus F, such that C plus F times C minus F is essentially FF. Then what one does is one replaces this by this formula, and then one can get exactly what's the period of this formula, and this gives an explicit recipe to construct the p-adic L function. I mean, let me write down this. So then you can exactly compute the p-adic L function. So essentially what you get is lambda f sim square g at 2k divided by g square times c plus f is this some explicit form constants. Then you get like f dk divided by c plus f. This is the first term, which is interpolable by Greenberg-Stevens. And then rest, you have a second term like mod d power k minus half divided by mod chd square. This you have to prove like a lambda-adic Shintani lifting, and then you can do it. And the rest of the term is like the Peterson product with the Saito-Kurokawa lift, and that also one can show that the lambda-adic Saito-Kurokawa lift can be interpolated. So this whole way essentially gives you the construction of the p-adic L function for this. And then finally you use this like standard trick, FF and GG square. This is nothing but like GG square times by my choice C minus F. And then since the periods also somehow match, this you get it for free. So because I did not tell, because for the, as I was telling, like for F G G at 2k divided by F F G G G G, this is then by Minglung Shea essentially. So yeah, so just a rough sketch, but this gives you some idea how to prove this. Okay, so in the last 5 minutes, let me tell a few words about how one can do this. And sorry, one remark, I mean, here, if you look at a bit closely, you would see the weight space, what the remark. Here, the weight space is really like a line, because I have taken like, yeah. So my weight space is 2k and k plus 1. So essentially, it's really a line. So one can actually generalize this to some two-dimensional space. So then what you have to do is you should start with S2kn, and G you take some Ln, where L, let's say, greater or equal to k. And then corresponding to this, we have a recent generalization of the spatial value formula, one then have to use the Shimura derivatives to construct the p-adic function to match up the weight difference essentially. So, yeah, I don't want to go into details. So now, yeah, just in the last 4 or 5 minutes, let me tell just a bit about what's the unbalanced situation. So yeah, so more difficult case. Is when this is -1. Okay. So what happens is, like, if we are in the unbalanced case, so then Minglung She has also constructed the unbalanced p-adic function. So one should expect something like this. Here, fortunately, we can still have our p-adic function. But the trouble is, now the interpolation regions are different. Because let's say, so for example, let's say weight 2, 2, 2. So this now lies outside the interpolation region of the unbalanced p-adic function. There is no way that you can just take the interpolation formula and prove it. Okay. So how does one then try to prove this? But let me just, since I am running out of time, this is actually still in work in progress. So, but for weight 2, 2, 2, what I am expecting is like LP unbalanced F, G, G at weight 2, 2, 2. This should be equal to like LP F sim square G at 2, 2, 2, and this is like LPF at 1. 1 is because if you remember, I had S minus K, so it will be really like the 1. Yeah. So this, now what is this guy? Because this I have no meaning in the interpolation. And that's where there is a fundamental result by Darmo and Roger. So they prove this, like, even though it lies outside the interpolation region, there is a p-adic Gross-Zagier formula, which relates this to some kind of Abel-Jacobi map. And then you take the, let me write this down first, like you take some cycle, which is known as Gross-Kudla-Shon cycle inside CH2X30, where X is like the modular curve. So then you evaluate at some differentials, like some, and this gives the p-adic value here. This, we are lucky because this is still in the interpolation region. But what we have to make sense of this one, and this is actually some kind of, one can show that this is a factor of p-adic, BDP p-adic function divided by some twisted L value. And this, this we have already seen something like this, like this will be again some kind of Abel-Jacobi map of some Higner points evaluated at some differential. Okay. So essentially, this again boils down to comparing the Gross-Kudla-Shon cycle.
Excuse me. So maybe what is compressed period in unbalanced case?
In the unbalanced case?
Unbalanced case.
This I don't remember exactly.
Okay,
I have
doesn't
to
matter.
see,
Doesn't
yeah,
matter, yeah.
I have to see it. Yeah, I'll tell you later. Yeah, so essentially this, I mean, sorry, I'm just over time. Just let me finish in just 1 minute. So essentially what it boils down to is like, so you have something inside Chow group of CH2x3. But on the other hand, I have some Higner point in CH1 of X. How can we compare, right? So there is a construction by Darmor or Sols, which gives, like, you can construct something PF, let me say Chow Higner point from this GKS, which will be inside the Jacobian. So then under some rank 1 assumption, so that's another important difference between the balanced and the unbalanced. Here I have to assume some rank 1 assumption on the Jacobian. And then I can have, like, this Higner point will be some constant times the Chow Higner point. And then somehow I have to find this explicit constant. But how can we expect to find this explicit constant? And this is where, I'm sorry for overloading, but this is where there is another thing you have to remember. If I take the complex derivatives at 2, this will be like lambda sim square g at 2 times L prime F1. So this is actually a result by Yuan Zhang. This is also like a complex Gauss-Jagier formula. This we know. And this is again exactly like this. This will be like a quotient of the classical Gauss-Jagier formula, which we also know. So essentially from here, we can exactly find out what is this constant. And then once we have this exact relation between these two kind of Higner points and the Chow Higner points, then I go backwards. Then I first apply the Abel-Jacobi on both sides, and then I lift the result to Chow CH2x3, and this will finally relate this whole equation. And of course, this is just a very minute part of the story because it's only at a single point. This you have to do at all the classical points. Then you can extend this to the full weight space, and then it will be done. Yeah, thanks. Sorry for the.
Any questions?
Sorry. Sorry. Coming back to the balanced case.
Yeah.
So you're discussing decomposition, and at some point you consider C plus F and C minus S,
Yes.
which are not canonical.
Yeah.
And moving in Hida family.
Yes.
So maybe I guess you need to introduce also p-adic period. And
Yes. Yeah.
Okay.
Yeah, yeah.
You do it.
I have a lot of. I mean, I'm skipping many details.
Yeah. Okay.
Yeah.
Okay.
Yeah.
Just to make sure.
Yes.
Okay.
Yes.
Thank you.
Absolutely. Yes.
I wanted to ask this construction of an L function for a tensor product of modular forms. Does it work in full generality for any number of forms? People seem to talk about triple products a lot.
Yeah. Yeah. You saw, like, in the morning, triple product lies in the center. I mean, for some cases, it's really like this is the most generic case in some sense. This will give you conjecturally many other conjectures. I mean, main conjectures and everything. I mean, this essentially is this Euler system. This I mean, this I'm talking about only this Gross-Kudla-Schonn cycle is in the weight 2, but in weight K, the Darmor-Rodger has the diagonal cycles. That's the Euler system essentially. So for, like, if you take, let's say, 4 Rankine-Selberg of 4 products, I don't know anything. There is no algebra. Yeah. Yeah, exactly. That's the first important point. Yeah. So for any p-adic L function, yeah. Yeah, the first step is the algebraicity result, right? So that's why for F tensor sim square G in the full generality, that's why we had to go through this full result. I mean, this is really like a general case, special case of like GLN cross GLN plus 1. It's like GL2 cross GL3. So this. This we have not yet considered. I think, yeah, that's a very important question actually, because somehow this factorization formula should give us more information about the exception. Yeah, that we have not yet considered. But that's, I mean, in Dasgupta's case, for example, that's what happens. I mean, but one has to be careful because the Euler factor for this this almost comes from the Euler factor from this one. So essentially, if you have if you don't have exceptional zeros here, then maybe it's difficult to assume to come from here. But that's an important point which we are still thinking. Yeah.
Okay, so let's thank the speaker one more time. Thank you.